Hello, everyone. So the next talk will be Provable Representation Learning by Professor Simon Du, who is an assistant professor in the Paul G. Allen School of Computer Science and Engineering at University of Washington. His research interests are broadly in machine learning, such as deep learning, representation learning, and reinforcement learning. Prior to starting as faculty, he was a postdoc at Institute for Advanced Study of Princeton. He completed his PhD in machine learning at Carnegie Mellon University. Previously, he studied EECS and EMS at UC Berkeley. He has also spent time at Simons Institute and research labs of Facebook, Google, and Microsoft. So over to you, Professor Simon Du.
Hi, thanks for the nice introduction. Just double check if you can see my slides and hear my voice.
Yes.
All right, nice. All right, hello everyone. So today I'm going to talk about some theoretical investigation about representation learning. All right, so let's begin. So we all know that nowadays neural networks are everywhere. It can be used in solving many computer vision tasks where we use convolutional neural network, in those bioinformatics tasks where we use graph neural network to model those, say, molecules. We use recurrent neural network, attention-based neural network for natural language processing. We use, generally fully connected neural network to those feature-based. For example, here we use this fully connected neural network for this housing price prediction. And lastly, we all know that neural networks be used in reinforcement learning. So basically, neural network has revolutionized like many applications. So today we'll talk about one particular usage of neural network is representation learning. So here, let me give you an example, like how representation learning is used in computer vision. So this is a procedure. So we oftentimes have a large number of data, like say this ImageNet data, where we have 1 billion data points, and there are, say, 1,000 classes. We can basically treat 1,000 classes as 1,000 tasks. So here we will train a representation. So basically here representation just means the mapping from the image to the second to the last layer, which is this layer. So here to train this neural network, we just use the data in ImageNet, where we have both label this input image and the label. And what's important to us is this mapping, or we can call it feature extractor, that maps the only image to a vector form, which is the second to the last layer. Okay, so this is what we call a representation of this image. So this representation is of a vector form, so that is like easier to deal with instead of directly dealing with this image. Okay, so now we have learned this representation. This representation is very useful because it can be used for other tasks. For example, here we have another, like image, possibly from another task, not in those 1,000 classes in ImageNet. So here, what we do is just we fix the representation. This representation is learned from using this ImageNet, and then we just train the last linear layer. So basically, we're just solving a logistic regression problem for this new task, and we classify this image as a dot. Okay, so this image can be very different from those in ImageNet, but here the representation we learned from the ImageNet can be still useful for classifying new images. But here, the only difference is that we need to train a new linear classifier. Okay, so this is like procedure how we use representation learning for computer vision. So here, let me give you a more concrete example showing how powerful representation learning is. So oftentimes we call those tasks that we train representation the source task. For example, here we can just use ImageNet data where we have 1 million data points to train this representation. We will train the second to the last layer. All right. So now we have a target task. That's the task that we really care about. So here, for example, we can consider this called few-shot learning task on this VOC7 data set, where there are only 20 classes, and each class only have 1 to 8 examples. So it's like very few sample per class, and there's a very few data from this image data set. Okay, so here's the result. If we don't use this representation learning technique, so we just use this few data from this target task, we can only achieve 5% to 10% accuracy. So this is not only for neural network, you can also try other methods like SVM or other feature extractors, but basically you can only achieve 5 to 10% accuracy. So that's pretty bad because, because we have a 20 class classification problem, but even if you just use random guess, you have 5% accuracy. But here, if you don't use representation learning, you can only achieve 5% to 10%. So that's basically just above the random guess. So now if we use representation learning, that is, we first use this representation learned from ImageNet, and we just retrain the last layer. So we can directly boost the performance to 50% to 80%. So you can compare these two numbers. You can see this is a huge improvement using this representation learning. Okay. So this is just one example from computer vision. Representation learning is a general technique that can be useful in other domains. For example, for natural language processing, sometimes we have this recurrent neural network model, and we can use this hidden state as a representation, and can be used for target tasks where we train this representation on a source task. And nowadays, graph neural networks are very hot. Can often model, say, molecules or social networks as graphs, and we can learn a graph representation for this entire graph, or learn a node representation like this that have each node has a vector form as its representation, and we can use representation for downstream tasks. That's very powerful as well. And there are many different types of representation learning. You can check out this paper by Benjo et al. In 2012, where it's just a good survey for different types of representation learning. Okay, so hopefully this quick introduction to representation learning shows you how powerful representation learning is. So my research focuses on the theoretical foundations of different types of machine learning methods. So here we really want to know is why, when and why, like this representation learning help. So for when, I mean that what are the necessary and sufficient conditions about the source task and the target task that make the representation learning really improve the accuracy. And secondly, we want to understand what is the underlying mechanism that makes the representation learning work. Okay. All right, so to study this problem, we do need some notations and the mathematical formulation. So this is our formulation. Okay, so if you have any question, please interrupt and ask, because this is really important to understand this formulation. So here we form this representation learning as a source task and target task problem. And you want to learn representation learning that can be useful from source task to the target task. So here, oftentimes we say we have total big T number of tasks. So for this T task, these are source tasks. I'll denote them as x1 to xt. These are the inputs. So for this T task, they share the same, when do prediction, they share the same representation, which we denote as H. Okay, so this H function first map every input from every class to a vector form, okay, which is the second to the last layer. And for different tasks, we can use a different predictor on top of this representation class. Okay. So the composition of, say, G1H is our prediction for the task 1, and GT, small th, is our prediction for the T's task. And in total, we have big T tasks. Okay. And for the target task, for example, here we train the source task using ImageNet, and for target task, we will use this VOC7 dataset. we'll fix this learned H function, which is a shared representation, and we just retrain this last layer, which is F function. So the composition of F and H is our prediction function for the target task. So in training, oftentimes we will model both G, F, and H. So oftentimes we assume say G and F belongs to some simple function class. For example, they're just linear classifiers. Okay, so here we use big G to abstractly model this function class for these predictors. And for this representation, small h, we assume usually it is a very complicated neural network. We call this function class, this class of functions of the neural networks, the representation class. Okay, so this is formulation. So more mathematically, so here we suppose we have in total T sort tasks, each have N1 data. So these are our data sets for the source task. And we use this source task to learn the representation following this bi-level optimization problem. So in the outside, we are trying to minimize with respect to some function, representation function within this class, such that given for a fixed representation class, and with different predictor on top of this representation, this can minimize the loss. So here loss, you can study quadratic loss or logistic loss. It's very easy to exchange different losses. So here for simplicity, let's just consider quadratic loss in this talk. Okay, so here basically we are trying to use this bi-level optimization problem to learn a good representation H. So this is a representation learning step. In the prediction learning step on the target task, over time we have, say, one target task, and we have very few data from this task, say N2 data, and they are sampled from some underlying distribution, say mu. And these data are denoted as X1TA, Y1TA to Xn2TA, and Yn2TA. So here we will fix this H, okay, from the representation learning step, and we just retrain the last layer, which is this F function, using this N2 data. So this is our prediction. F composition of F and H is our prediction function for the target task. All right, so this is our formulation. Basically, this is an abstract form of the representation learning step. All right, so let's to illustrate the theory. Let's first give you a brief review of the standard statistical learning theory. So suppose we only use this N2 data to train this target classifier, then we'll have we need to solve this optimization problem. So we'll optimize both F and H and trying to solve this optimization problem. So the standard learning statistical learning theory can tell us this is the expected loss or the generalization error. It's of this form. That is, it is in the order of CH plus CG divided by N2. So CH and CG, there are some complex measures of the representation class and prediction class. So usually the representation class is very complicated, and prediction class is very relatively simple. So CH is often much larger than CG. So these complex measures are general notions. For example, there can be number of variables with dimension, number of complexity, and Gaussian weights. These are some complex measures for different function classes, and they can be used to model neural networks as well. All right, so this is the standard statistical learning theory, and you can see here only if you have a large number of N2, so you can have this term to be small. Okay. But in practice, N2 is often very small, so we need representation learning. So here, our ideal theory for representation learning is following. Want to identify a set of, say, natural assumptions, such that if the data satisfies these assumptions, then representation learning probably helps. By probably helps, it means we can probably improve the sample complexity compared to this standard learning theory that's only used for only using the data from the target domain. And secondly, we want to show, without this assumption, representation learning does not help. So to justify, this kind of assumption is kind of necessary. So this is a target theorem that we are shooting for. Basically, we want to prove that the rate or the loss or the generation error is of this form. That is CH divided by N1T plus CG divided by N2. So let me expand these two terms a little bit. So why, instead of dividing by N2, here we have N1T in the denominator? Because in representation learning, we are really using the total N1T data from the source domain to learn this representation learning. So ideally, if we want to identify a set of assumptions such as under which, we can basically use all the source task data to learn this representation. That's why we have the first term, that is CH divided by N1T. And second term is basically for counting, we use this N2 data to learn the final layer, this prediction task specific layer for the target task. So you can see here, compare with the standard learning theory that only uses N2 data to learn the predictor for the target task. This is much better, especially when number of tasks is larger. Okay, so this is the ideal theorem we're shooting for. So now let me discuss about the assumptions. The first assumption is pretty natural. That is the existence of a good representation. So at an intuitive level, this basically means that there exists one good representation function that is good for both those source tasks and the target task. So mathematically, this means that there exists a representation function H star in this big H function class, such that there exists some predictors G1 star to GT star, these are for the source task, and F star, which was target task, such that the composition of this predictor and representation have very small loss. So here we assume they have zero loss, but you can generalize our results to a small loss. So the small loss holds for both the source domain and for the target domain. Okay, so here we have expectation with respect to the underlying data generating process. All right, so this is a very intuitive assumption, because if we do not have this assumption, basically cannot hope that representation learning work, because this is exactly how we use the representation learning practice, that we fix a learn representation that is good for both source and target tasks. So we must assume that there exists such a good representation. Otherwise, we cannot hope that representation learning can help. So this first assumption is pretty natural. The natural question is that whether this assumption is already enough for illustrating the theoretical benefits of representation learning. So somehow, unfortunately, that we can show this existence of a good representation learning is not enough. So here's an intuitive example. So suppose all your source task is about classifying different types of cats, okay? And your target task is about classifying whether an image is a cat or a dog. So in this case, you cannot hope that representation learning can help, because source task can give you a very good representation function for representing these cat images. Okay. And if a new task is also related to cats, then you can believe that this this representation learning is helpful. However, because there's no dog images in the source task, you cannot hope that this good representation is also useful for the dog. Okay, so this is an intuitive example that why only assuming there exists a good representation is not enough. You need to have some dog images in the source set so that you can find that good representation that you also use for the target task. So here's a more formal counterexample. So suppose you have input that is 1000 dimensional, there are just 0, 1 vectors, and the good representation is the first 100 dimension. Okay, so by good representation, I mean that all the tasks, both source and target tasks, they only need to use the first 100 digits for the accurate prediction. For example, the task can be predicting, whether the 10th digit is 1 or 0, predicting the sum of the first 100 digits, etc. So the best scenario is the following. Suppose the source has only used the first 50 digits. They're only about whether the first 10th, whether the 10th digit is 1 or not. However, the target task, you need to use all the first 100 digits. For example, predict the sum of 100 digits. So in this case, the source task cannot give you the full information about the good representation. Like here, the source task can only give you information about the first 50 digits. But from the 51 to 100 digits, from the first task, you don't know whether it's good representation or not. Only using the source task cannot get any information or useful information for the 51 to the 100 digits, which are also necessary for the target task. Okay, so hopefully this two kind of example give you a sense that only assuming there exists a good representation is not enough for the representation learning. So we need some additional assumption that really make this to expand why representation learning can work. So this proposed assumption is called diversity of the source task. Okay. So basically, from the previous two content examples, we know that representation learning is useful only if the source task can give the full information about this good representation. Okay? By full information basis is a sense of the diversity of the source task that can cover the entire good representation. So now the key question is, what is the definition, the mathematical definition of diversity? So after some mathematical derivations, we can arrive at this assumption. Okay, so here let's consider a special case that the last predictor layer or this G function class is a linear prediction function. So now the assumption 1, the existence of good representation, becomes this one. So basically, we just replace composition of G and H by a more concrete form, which is an inner product between a linear vector and its representation function. So here the representation has the dimension k, which is, we assume that it's much smaller than, for example, inputs. That's why we need this representation. So the definition of the assumption 2, diversity of source tasks, for this function class linear predictors is the following. So basically, we just concatenate all the optimal linear predictors. So remember, we have to have T source tasks, so we have T linear predictors. So these are W1 star to WT star. The diversity means this matrix, which is a K by T matrix, is full rank. Okay. So here full rank, we mean it has rank K. So we here implicitly, we actually assume that T is bigger than K, so that this matrix can cover the span of the good representation. So intuitively, this assumption just means when T is bigger than K and separate star, big W star is a full rank matrix, then this cover, and remember our representation is of K dimensional. So if it's full rank, basically this linear predictor, optimal linear predictors cover the entire span of the good representation, which in other words, it means this source task contain the whole information about this good representation. So based on these two assumptions, we can actually derive several interesting theorems. So for example, let's consider as a warm-up, we consider linear representation class that the representation is just a linear function or like a matrix. So the assumption becomes that your prediction is just a linear product between WT star and B star XT, where B star is the optimal linear representation that maps a high dimensional input in D or D to K dimensional input. So this is called a linear representation or subspace learning. And our prediction is a linear product in WT star and B star XT. And for the target task is WT star, the linear product between WT star and this B star XTA. So it's the first assumption. And second assumption is just this W star has a full rank. So this is our key theorem. We can show that under these two assumptions, generation error of the following form is dk divided by n1t plus k divided by n2. So first, for this dk, this is basically the complexity measure for learning this linear representation class. And second term is just using n2 data to learn this k-dimensional linear predictor, WTA star. So the first time to learn this B star, which we can use all the data from the source domain, which has n1t data points, and the complexity measure is dk. So that's why we have these two terms. So comparing with the case that we dealt with representation learning, basically you are trying to learn a linear predictor. You have d over n2 data. Classification error rate. So when the n1t is much smaller, much bigger than n2, then using representation learning is much better than without using representation learning. All right, so this is the first case. We solve some theorems for some general function class, including neural networks. For a general class, we use this a complex measure called Gaussian width to measure the complexity of this representation class H. So here we have this classification arrow bound, or this generation arrow. It is CH, which is the Gaussian complexity of the neural networks. There are also bounds for the Gaussian complexity for neural networks. So the first term is CH divided by n1t. So again, we can show that we can pull all the data from the source domain to learn this representation. And for second layer, second term, we can use the n2 data to learn this k-dimensional linear predictor. All right. So again, this is the ideal theory you want to have. So just a quick comparison with the previous work. There's a paper by Mauer et al. In 2016. They show that they do not have the second assumption. So they also have the first assumption, and they also have another assumption that all the tasks, both source and target tasks, are ID sampled from a distribution of tasks. So this is a kind of a probabilistic assumption. Instead, our assumption is more deterministic. But under their assumptions, you can only show like a dk over t classification error rate as the first term, instead of say n1t dk over n1t. So here you can see under our assumption, this is more natural because we can show that we can really use all the data from the source domain to learn this good representation. But here you can see there's no n1t in the denominator, and this shows you cannot use all the data to learn this representation. And actually, in their setting, they can show that only using this assumption, this n1 over t is tag. So this also means that our assumption is more natural. If you want to demonstrate that you can use all the data to learn the representation. So now we want to understand why this works. So what is the underlying mechanism to make the representation learning work? So this already comes from our proof. So intuitively, the main idea is the following. So here we are trying to find one representation H that can be useful for all the source tasks. Okay, that's why we are solving this minimization problem with respect to H. So here, in our proof, we can argue that we must find a shared good representation that is useful for all tasks, because otherwise, the loss cannot be small. Okay, and this joint opposition in this form actually forces the learner to learn a good representation to make this loss small for all the tasks. All right, so the key messages are the following: that the existence of a good representation and the diversity of the task. These are the two key conditions that enable representation learning to improve the sample efficiency. Okay, so this is a key message from these talks. So briefly, I'll talk about some extension. There's one extension called linear bandits. Basically, you have t tasks. Each round you can choose t actions concurrently. In total, you have n rounds. And we assume there's a finite stochastic actions, and you have some reward that is linear. But there you have a shared linear representation B star. And again, just like our linear case, we have some WT star that is useful for all tasks. as for each task. That's a task dependent. So in terms of theory, we can prove some regret bounds, showing we can have this kind of regret, that's a square root bkn divided by t plus square root of k big N. So it's much better than the naive algorithm, which treat each task like independently, which is square root of d big N. So this is another example showing, under these two assumptions, you can show probably improvement over the naive algorithm. So in our paper about some experiments on, say, amines data set in a suspended setting, and we can see here there's a lot of improvements there. All right, so in summary, this talk about when and why does representation learning help. The key message is that the existence of a good representation and diversity of source data, these are two important conditions. And this joint optimization is the reason why we can learn that good representation. So the open problem is that here we only understand it through the statistical point of view. We haven't understand it through the optimization lens. So here for future work, we want to understand what is the optimization theory for representation learning, especially these optimization problems, they're all non-convex. And we can also study representation learning for other settings. We talk about bandits, but there are other settings that are natural to study, like reinforcement learning, control, and many others. So to conclude here and see if there's any question.
So, so do you have any questions from the panelists? Okay, so I had a question. So suppose we were to think of these tasks, right? Like say the data sets, I do adversarial perturbations of a single data set and then generate some of them, right? And I mean, so when you are sort of asking for the adversarial sort of loss where you would want to put a max over the no x belongs to the the adversarial ball around, right? Whichever way you would want to do. I mean, are we somehow can we kind of get an equivalence for this between this formulation and suppose you measure the loss when you take the max over the data, or is it that we are getting away because we are sort of taking the summation, right? The summation over all the tasks because it's a summation. Are we getting around getting away because it's not the max anymore, but it's sort of the average thing? And I mean, is there an equivalence? I mean, here.
That's a good question. I'm not. I guess it's not equivalent, especially in terms of analysis. Definitely, is different. However, I think even if you use this kind of max loss, you can still under some assumptions, maybe same as ours, you can still show you can transfer the learned representation, because intuitively, basically you need to as long as your object function can force the learner to learn a good representation that is good for all the tasks. I think the max also have the same effect. So it can be used there to, this max loss also can be used to force the learner to learn this good representation. I think that's a very good direction to investigate.
Yeah, I mean, I also had a slightly related question, right? Like, Alexander Madry had this experiment where so you take the representation. I mean, you take a dog and then you just perturb it, and then so that it becomes a cat, and then you actually label the data set as the cat, but actually it looks like the dog, and then you train on that, right? Like, and you'd still get good accuracy on the original test set, which is the unperturbed test set. Like, I mean, is there any anything that we could take? I mean, where he's basically saying that he's making a distinction. I mean, distinction between robust features and not so robust features, right? Like, is there a way where we can sort of connect the
right? I think that's a very good point. So so here we just analyze this like straightforward formulation. So in there, I think in their technique can force you to learn good representation more efficiently, especially using this kind of purification step in Squid Marjorie's paper. I guess under some assumptions, you can actually show that, for example, even better than this kind of convergence rate using their technique.
Okay. So, but do we get good? I mean, when we so we know that these neural networks fit Gaussian noise, right? Like, I mean, even Gaussian noise as input. I mean, do we get good the CFH? Is it good? I mean, is it not backwards, or it's okay in general? I mean,
yeah. I mean, nowadays people have developed some this kind of bounds for neural networks. I mean, yeah, definitely there are many that have vacuous, but some are not vacuous. So here, our paper is a general framework. You can plug in whatever those theoretical results. So you can pick the tightest one, so that will be not
for anything
the vacuous one.
Okay. So yeah, there are. So yeah, so there is a related question from one of the attendees, which is like, if you have a good representation of the source task, for example, all types of cats, how do you deal with adversarial images in the source task? Right. So
okay. That's I mean, I think in the source task you can still change the. So there are many ways kind of people have developed to deal with this adversary. For example, you can add some additional terms, regression terms, or you can train the training method in the source task. So here we assume that basically we just we can solve the optimization problem. However, in solving the optimization problem, you can using for example more robust way to solve it. For example, using adversarial training, or adding some additional representation terms that can deal with the adversary. So yeah, I think there's a many place to play around to to make this more robust. Here, this is a standard, for example, statistical learning setting, but you can make it more robust using techniques from this robust learning literature.
Okay, so I think there are no more questions. So yeah, thanks again. Let's thank Professor Simon Du for the great talk. Thanks again.
Thank you.
Yeah. See you there. Yeah.
Thanks, Chandru. Maybe I'll take over now for a while.
Yeah, sure.
Okay, thank you. Thanks, Chandru, for sharing the session. And I would just want to take a couple of minutes to wrap up the conference and give some closing remarks. So yeah, so we've had 3 great days of great talks. This is the first conference on deployable AI, and it's been amazing to hear all these eminent speakers over the last 3 days. So I just thought I would take a few minutes to thank the people who are involved. First of all, of course, thanks to the great keynote speakers, Subbarao Kambambati and Professor Samuel Kasky, who gave great keynote talks. And also thanks to all the invited speakers. I know a lot of speakers had their talks in their time zones much later in the night or much earlier in the morning, but then they still agreed to talk here. Thank you very much to all the invited speakers. I mean, we had a wonderful set of speakers and great set of talks over the last 3 days. And of course, I should thank the organization team, the general chair, the program chair, my co-program chair, Balaji, the general chair, Professor Ravi, and the program committee, who did a great job in reviewing the papers that were submitted to the conference as well. And of course, the big thanks to the entire team at RBC DSI, who has been, running this conference, starting from Sridhar to Martina, Divya, Philji, Sendamir, and Vidya. I'm just going to go over the names, because they've done an incredible job here. Shreya, Tarun, Manoj, Mohit, Sumant, Siddharth, Shruti, Karthik, Gokul, Mohit, Raj Pandian. I'm sorry if I had missed somebody's name. So all of these people have kind of been instrumental in running the conference over the last 3 days. Right, not just the last 3 days, right from the inception of the conference itself. So a big thanks and a big shout out to all of these people. Of course, a big thanks to all the audience who have been attendees who've been asking great questions, and I hope all of you enjoyed the conference. It would be great for us to get feedback from all of you to understand what went well, what did not go that well, and so on, so that we can keep improving and providing world-class content in the next coming time as well. Right, so please take some time out to fill the feedback forms. It was shared in the chat, and it will be shared again so that it will be a clickable link. Couple of last few things. So for people who have been asking about participation certificates, I think we would need a couple of days to tally this, make sure we do it right, so that by end of day Monday Indian Standard Time, you should be able to get your participation certificates. And there were a lot of questions about whether these videos are going to be available somewhere. Yes, we'll make them available on the Robert Bosch Center's YouTube channel. So do visit the channel maybe after a week. So we would hopefully get the consent from the speakers to upload these videos, and it should be up in a week. Okay, I mean, I would like to express my thanks to everybody at RBC DSI, and please do take a moment to check out the great work done by RBC DSI. I mean, you can check out the social media pages of RBC DSI to know more about the events that are happening and that will happen in the future. Okay, so with that, I think we come to the end of this conference. I hope all of you enjoyed. Thank you very much to everybody who made this possible, and have a good night. Thank you.